sort of the beginning of the technical portion of this lecture, of this course. One thing before I start is this is the number of open invitations for the blog. I feel like I'm giving a party at my home and 22 people have not come. They have not accepted the invitation and they still want to get a grade in this course. That's not good. Okay? So if your name appears anywhere here, that means you haven't actually gotten onto the class blog, you're in trouble. You should be already signed in. I would remove this, don't worry, before I put it up on this thing. But there are about 22 people who haven't yet gotten on, and there would be required assignments that you have to do on the blog, and I'm not going to be wasting my time trying to make sure that you will get onto blogs after the first week is over, and the first couple of weeks are over. Okay? So please do it now. I'm pretty sure you have time for that. And then I also started this tweet notes thing, and we know at least 2 people who get reasonable grades in this course. The rest I have no clue because they are not tweeting any notes. So since everything has to be converted into points, we will say that each student must send at least 1 tweet note for at least 2/3 of the classes. That's the new rule. That's the participation. Remember we said we have participation credit in this class? Okay? Yeah.
What if you don't have Twitter?
What?
What if you don't have Twitter?
You read what I said. You just send an email.
Okay.
Okay? There was an email sent. Did people get it? I sent an email. It's not that hard. I'm not an unreasonable guy. I don't know how to tweet. Okay? So I won't expect you to do it. Although I expect you guys are much more like up to date than I am. All you need to do is send an email to an account I suggested, and then that would just get posted directly. Okay, that's basically what that means. Okay, are there any questions before I start? Okay, last class we basically talked about the fact that we will be looking at several traditional areas and how they get used in the web, right? So the first one, of course, is information retrieval. It's probably a central topic for this course. And so we are, for this next several classes, until I tell you otherwise, we are on this part of the information retrieval slide. Okay? So we're trying to understand traditional model for information retrieval. Okay? And then we will talk about how to extend it to make it work in the web. I realize that several of you already know information retrieval only because of web, but try to think in terms of traditional information retrieval, the problem that we discussed in the class. Okay? So that's what we're going to do today. And then the parts of the agenda essentially is, first we'll talk about what the problem is, and then talk about how to evaluate an information retrieval system if it works. Okay, before you go ahead and make a solution, you want to know what's the performance metric. What if your system works? How do you know that it's working? Okay, that's where we'll talk about precision and recall metrics, which we discussed already, but we'll kind of formally discuss it today. And then we will talk about the most important idea in information retrieval, the most ill-understood idea in information retrieval called the relevance. And we'll talk about what the relevance is supposed to depend on, and how to compute it correctly, and how we'll give up computing it correctly and instead do something easy. Okay? So that's part of understanding in the class here is realize that actually relevance is something that's pretty hard to compute, and that we will eventually approximate it using similarity metrics. And you need to understand why we are doing, how we, what the true relevance is and how we convert it somehow into similarity metrics. Okay? So that later on, if you want to improve relevance, you should do the right way of doing it. For now, we'll just sort of do it as a similarity metric. Okay? So that's and then of course, after that, we will get into the stuff that you have probably heard about, which is Boolean similarity, vector similarity, Jaccard similarity, etc., etc. Because now we decided that IR is just similarity, we'll talk about how to do similarity. Okay, so that's how the lecture will progress. Okay, so what is information retrieval? Given a large repository of documents and a text query from the user, you want to return the documents that are relevant to the user. That's all. Very simple. Okay, now it almost looks like it's like a database problem. You know, if I were to say what is a database problem, the database problem is given a large repository of records and an SQL query, return the tuples or records that satisfy that SQL query. One and the same problem, and yet there's a world of difference. And the world of difference comes because the text query does not directly specify what the user wants. Okay, the text query does not directly specify what the user wants. In a database kind of a scenario, if I give an SQL query, I get to write 2 pages of it. If I made a mistake, so be it. The system will actually evaluate the SQL query I gave. And the system never has to ask me, are you happy with my answer? Do you understand what I'm saying? So it's like if I give you what is 7 plus 7, you will just give me the answer. You don't need to say, do you like my answer? You know, you're beyond that. You know 7 plus 7 is 14. Okay? So user has no real role to play in databases. This was the point I made last time. And in fact, all that you need in databases is which database comes back faster with the same answers. But now we are saying that the user is giving a text description of what they want, and it is expected to be imprecise for 2 different reasons. Imprecise because really to do this problem correctly, you may need natural language processing. So if I really give you what I want in a 2-paragraph long text, maybe somebody who understands English or my language can understand what I'm looking for and exactly satisfy me. Since most IR systems don't do NLP, they're trying to get by looking at that text without understanding its meaning, somehow trying to figure out what documents are relevant. That's one reason for imprecision. The other reason for imprecision is, over a period of time, if I know that you don't anyway understand what I'm saying, I'm not going to use GRE style vocabulary anymore. I'm going to talk nonsense because I know that you are anyway going to take my entire paragraph and only hear a couple of words here and there. So I will slowly start talking in pidgin English. I'll start saying a couple of words instead of saying the entire paragraph. Do you understand what I'm saying? Okay, so it's a kind of a co-evolving system where originally, you know, the users might like to say, you know, here is my need, and you know, here is a 1 paragraph or you know description of my need. And then you find that the system doesn't understand a thing. It just gives you a couple of pages. Over a period of time, you realize anyway it doesn't understand it, so I don't need to be particularly precise. So I'll just say a couple of words and let's hope that the system understands. So in both ways, the queries are imprecise. Okay, so the user has the most important part of IR is the cloud ahead on top of the user. And the user basically has something that they're looking for. Sometimes they don't even know what they're looking for. If you're a database guy and you don't know what you're looking for, you say, well, first I have to figure out what I'm looking for and then write an SQL query. But you know, in IR you say, you know, you don't necessarily even know what you're looking for, or you know what you're looking for, but you just express it imprecisely, just as a few keywords. Suffice it to say, in the end, these keywords somehow are only like a projection, a weak projection of what the user really wanted. And from that, you need to figure out what the user really wanted and give the documents that the user would find relevant. That's what makes IR hard. It's this imprecision of the queries that makes IR hard. Okay, otherwise it's database problem it's solved. Okay, so it's different from databases because of course the text, the records are not structured. You basically have documents, it can be written in natural language. Information, and you're looking for sort of text, you're looking for textual documents and you're giving textual queries, and the textual queries probably are not precise. For all these reasons I mentioned, it's not just one single reason. Because the system doesn't understand NLP. Because the users know that the system doesn't understand NLP, so they start talking nonsense. Because many a time, you know, the users don't even know what they're looking for, so they start giving a few keywords and hope that they will be satisfied anyway. Okay? How dare they do that? In a database, they won't do that. But here we just said, yeah, anybody can ask queries and believe. Okay, so that's the setup we have. Okay, so in principle, even if you have precisely expressed queries, doing IR requires NLP. But in some sense, we're trying to get by without having to do NLP, natural language processing. Okay. And then the other catchment is, since IR doesn't do NLP, users tend to write cryptic keyword queries. Since you don't understand, I mean, did you ever find yourself talking in iambic pentameters to your dogs? If you do, you need real help, okay? We normally tend to talk in short sentences to the dogs because first of all, we should realize that dog only understands dog's name. When you say, you know, blah, 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 the dog's name, blah, 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 that's all it understands, just the dog's name, okay? And so over a period of time, you realize this, and so you don't really talk in page-long, you know, careful sentences to your dog, right? And that's basically what you're doing. You think of your IR system as your dog, and so you just give a couple of keywords. Except, you know, if the dog doesn't do what you are expecting it to say, it's a bad dog. The same thing you get to do for the IR system. If it doesn't give you the documents you are finding relevant, you get to say bad IR system. Whereas if it's a database and it doesn't give you the query, the tuples that you know are the answers to this query and you know are present in the database, you don't just say bad database and leave it. You take the whole database, throw it out the window. Because that's the definition of the problem you are supposed to solve. Okay? Fine, so that's IR problem. And so as I said, IR, information versus data retrieval, you know, essentially it's a precisely defined problem. Information retrieval is an imprecisely defined, under constrained problem, imposed problem. Most interesting problems in the world are under constrained and imposed. So is IR. Okay? So that's what, and so of course, since it's imposed, obviously, as I said, small errors are tolerated by the user. So now we only say to the dogs, just because they don't understand, we don't start hitting them. You know, I mean, if you do, don't tell me about it. And the point is, you just say bad dog and move on. Okay? And similarly, if the IR system doesn't give you the answers that you're hoping for, you just get to say bad IR system and ask the next query. You don't take it personally because you didn't pay for it much, right? I mean, you basically yourself, gave a very precise query. Okay, so this won't happen in database systems. And then also one other thing that you want to know is, since there is like a whole bunch of keyword, documents, it tends to be the case that in databases, right? If I give an SQL query, all the records that satisfy SQL query are equally valid answers. And any record that doesn't satisfy the SQL query is equally invalid. Right? Okay. Whereas here, you're only trying to guess what is relevant and not relevant to the user. So you might want to rank the answers. Okay, the ranking comes up because I have no real clue what you're looking for. And we also have established that since you know that I don't have any clue as to what you're looking for, you then eventually start saying, asking queries even when you don't know what you're looking for. Okay, and so the only way we can play this game is I were to rank my answers. Okay, and then who decides the relevance? After I rank my answers, when I say I the IR system, a computer program. Okay, so if I were to give you the ranked list of answers, you the user, can I just say these are quite relevant? I'll give myself 100%, in the work well done, and I get to go to sleep. I don't get to do that because I don't know really whether or not they're relevant. You know whether or not they're relevant. So in some sense, unlike database systems where they can, as I said, 7 plus 7 is 14, you can check this without even asking me, did you believe my answer? Whereas if I'm showing you what I think is what you're looking for, then I have to ask you, is this what you're looking for? And so relevance is actually always established by the user. The true relevance is established by the user. Okay, so suppose this imposed problem, suppose I made a system for solving this. So it ranks a set of documents that it thinks might be relevant to the user and shows it to the user. Now, I made one and one of you made another system, which also tries to solve the same problem. Which one is better? How do I evaluate? So first, I want to talk about how to evaluate IR systems. As I said, for databases, the evaluation is there is a requirement that cannot be relaxed at all, which is soundness and completeness. That means all answers that are answers to the query are given, and no answer which is not an answer to the query is given. And that's for required. Otherwise, you won't even be allowed to enter the room. And so then the only difference between my database system and my friend's database system is one is faster, one is slower. Okay, or one is cheaper and one is costlier, or something like that. Okay, here on the other hand, we are getting stuck even at whether or not they're solving the problem. Okay, and so we talk about precision and recall, which I already mentioned. I'm going to re-mention it again. So the idea is, suppose this is the universe of documents. This rectangle is the universe of the set of documents. Okay, of these, the user. Remember, the user knows what they are looking for. Hopefully, let's hope that. Okay, so the truly relevant documents for the user, let's assume, are in this circle. That's the set of truly relevant documents. And then they basically, remember this picture, they had some actual true query. They sort of converted it into an imprecise query and gave it to the system, which then did some gobbledygook with it and gave a list of answers. Okay, so this is really, for an oracle who is not Larry Ellison's, but the true Delphic one, which is above both the user and the system, and is looking at this entire situation, it might know that the user really believes these are the truly relevant answers. Obviously, user doesn't know which answers are available in the document collection. So only the oracle will know that if in fact the document collection were to be made completely explicit to the user, and the user has no work to do other than to go through all of them and say this is relevant, this is not relevant, then this red circle would contain exactly the set of documents that the user ultimately found to be relevant. Okay, and then this green circle is the set of documents that the system actually returned. In general, these sets would be overlapping. First of all, I hope they are overlapping. If they are disjoint, then we are in kind of generating some random system. So we hope they have non-empty overlap, but they also have stuff here and stuff here. Okay, so this is the true positives. These are the documents that the user query. These are truly relevant to the user, and the system also returned it. And these are the false positives, in the sense these are documents that the system returned, but the user doesn't really want them. They're not relevant. Okay? And these are the false negatives, in the sense these are the documents that the system did not return. But if it returned it, the user would have said, yeah, they are relevant. Okay, now what I really want to do is to essentially make, in the best IR system is one which makes these two sets exactly equal. So it should be the case that TP should be equal to the size of the red circle. Okay, so in particular, and then similarly, Fn should be empty. At that point, Fn should be empty. Okay, so we define these two notions corresponding to soundness and completeness, now called precision and recall. Precision is the fraction of the documents that the system returned that are actually relevant. So that would be TP, which is this part, by TP plus FP, which is the total set of results you get. Okay, so the fraction, when you keep talking, the fraction of time you are actually saying sensible stuff. That is precision. And the recall, on the other hand, is TP, which is the fraction of truly relevant results by the number of truly relevant results you returned by the total number of truly relevant results. So what fraction of truth did you actually hit on while you kept talking? Okay? And obviously, in a fully sound and complete system, precision would be 1, recall would be 1. And if you talk in terms of percentages, precision would be 100%, recall would be 100%. And by separating this, you allow systems to be only sound or only complete, or little sound and little complete. And that's what precision and recall allows. And as I mentioned last time, so 1.0 precision is soundness, which is sort of like nothing but the truth when you take a vote in the court of justice. And 1.0 recall is completeness, which is the whole truth. I will tell the whole truth. I would not miss any relevant document. Okay? So that's precision and recall, by the way. Okay? And one interesting thing we'll talk about in a minute is, suppose I give you a system which has high precision and low recall, and another system which has low precision and high recall. In essence, which can you tell? If the system I gave you has, can you tell whether a system that I gave you has high precision? Whether the system I gave you is missing precision or missing recall? Which one would you be able to tell just by experiencing the system for a while? Do you guys understand that? As I'm talking right now, you have no clue whether I'm telling you everything that's important about IR. All you can tell is whether I'm making sense in what I'm saying. Do you understand what I'm saying? So precision is the only thing you can tell. As I'm talking, is he saying something relevant? Or is he just going on and on about his dog? Okay? And that's the only thing you can tell. But I might be completely missing important topics in IR, which I am sure I am. And you'll never know. Not while sitting here. Unless you go back and read Wikipedia and say, my God, I wasted an entire 6 months on this guy's course and he didn't even teach me this topic. Do you understand? And remember one time when I said, which is important, precision or recall, several people thought precision is important, and I almost had to look for devil's advocates pushing for recall. Do you remember that? Recall is the thing that you will never know you missed. Precision, you can actually tell if you're missing. Okay, there is an actually interesting argument that somebody has made. There are a lot of people here, grad students, and one of these days you'll start writing papers, and then they will conferences and journals select papers, some subset of them, to allow them to be presented in the conference. Okay, now obviously, truly good papers are known to the oracle. It's like the God's proofs. Okay. The program committee members who decide whether or not a particular paper gets in are essentially like IR systems. They're trying to just come up with some set that they'll take and the rest they'll throw out. So obviously they will be letting in some papers which are actually have no business being heard by any human being. And so then obviously when they're being presented in the conference, people sleep. But there are also papers that they don't accept, that should have been heard, and nobody heard them. So which is important for conferences? Obviously, to some extent, conference chairs have to think about recall, because precision, the people will vote by their feet. If the talks just keep dragging on and on and on, the people will leave the thing. But they won't know what they missed. So it's an important issue. And to put this completely in perspective, it turns out that this particular argument was made in SIG-IR, which is the best conference for information retrieval, which in 1998 rejected the page rank paper because it wasn't good enough. Okay? And it turns out that the way you decide whether or not a conference is good is not based on how many cookies they give during the breaks, but based on how many people wind up citing the papers that are published in those conferences when they write their own papers. So if you take the total sum of citations to SIG-IR papers, that's sort of probably just about equal or less than the number of citations to page rank paper. And yet they threw it out. Now it's very easy for us to say, what bozos, but hindsight is always 20/20. We didn't know at that time, and the people didn't know. I was not on the program at that time. Okay? They didn't know at that time. And what they did was they ensured precision, and they lost out on recall. This should make graduate students happy that if everybody increases recall, then all our papers will be published and then we can get our degrees much faster. But that's a different story. So, whose absence can the user sense? Remember, precision. Which also means that if all you want to do is sell a system, you want to make sure that you work on precision. Because if they're missing recall, they would not know. So all I need to be doing here is to be funny and sort of act like I'm being relevant. And it'll be too late by the time you'll realize that I didn't teach you anything useful. Do you understand what I'm saying? That's the joke of precise teaching. I had an electronics teacher who was one of the most charismatic teachers, and he was extremely good at making sure that we got all his fears of electronics. So even now, if I look at a big electronic circuit, I don't know what to do with it. Okay? But I loved the class. It was a precise class, a lovely class. I enjoyed the class, but I didn't necessarily learn what I'm supposed to learn. And you will never know whether you're learning what you're supposed to learn or not until the class is over. So if I want to make the class interesting to you, or if I want to sell you a search engine, I should work on the precision. If I want to think of longer term issues, I need to also think of recall. Okay? Yes, there was a question. Yes.
If a search engine claims that I have this much precision and this much recall, how do we actually verify whether, because how do we know what's the TP value and FP value?
That's basically based only on so what they have to do is some third party has to do, the only way to evaluate this is third party has to do over a corpus of documents and queries, oracular precision and recall studies. Because remember that to know the red circle, you need to know what is actually relevant to the user. So in fact, that's a good question. In fact, let me see if I can get to that slide and come back to this screen. Yeah. And that should be, I'll go back after this slide, which is how do you, so basically, the IR conference has a competition track called the track, text recognition track. And basically people will make their IR systems and then they go through this competition. The question is, how do you decide which system is winning? The way they do it is how do you evaluate information algorithms need prior relevance judgments. And so basically for each query, and they have a set of documents that they hold it constant. And they make up a bunch of queries. For each of these queries, they do focus groups. Okay, so get people, grad students, undergrads, people on the street, and say, if this were the query, which of these 10 million documents you consider relevant? So obviously it has to be people who have no other work to do, who will then do this kind of focus groups. Which of you have been in focus groups for the TVs? At least anytime Nielsen calls me during my dinner time, I never took part. So obviously you cannot blame me or thank me for the situation in American television because I never gave my opinion. Okay, and the same thing, track will ask some people to give their relevance judgments. And they assume, obviously, that all users are created equal, just as Nielsen assumes that all users are created equal. They're not, but that's the only thing you can do. Okay? So, and then you will get the relevance judgments on the documents for a set of queries from the random users, and then you hold it. Okay? And then you give the same queries to the IR systems, they will give their top 10 or top 100 results, and then you can compute TPTF. And then you can talk about precision recall. Do you understand what I'm saying? So that's how track is done. Okay? Track is an actually known competition where they take time to do this. Now when search engines say this is highly precise, etc., hopefully they are doing some sort of an oracular studies. The only way to evaluate it is this way, third-party evaluation. Okay? So now actually I will shift this back to that place later on now, but I want to go back to my old slide. And then say that, okay, now you should know answer to this. Why don't we use precision recall measurements for databases? Because the only precision recall measurement that makes sense for a traditional database is 1-1. Everything else is not called a database. Now it turns out, of course, we'll talk, as I mentioned, in the database information integration slide last week, databases are, the people using online databases are no smarter than people using online search engines. And they're still asking imprecise queries. And so it turns out precision recall is still the right measure for online databases. They're not for the traditional databases. Okay. Now, one interesting question about the precision recall is how does precision change as recall increases? Okay, so people actually draw these curves called, rather than just give one number for precision and recall, you want to provide more of a finer grading on how is the precision changing as you keep talking. Most of us tend to lose precision as we keep talking. I might be able to go on for about 3-4 hours, after which, I still make a lot of sense, but you probably think I'm not any longer precise. Okay. So in general, you expect precision recall curves to go this way. Okay, and the x-axis is recall, which is, let's say, 0, 0.1, 0.2, 0.3, etc., up to 1.0. And then y-axis is precision, which is 0.1, 0.2, etc., up to 1.0. And the question is, how is precision changing with respect to recall? And those are called precision recall curves. And that sort of gives you all the information you want about an IR system. Okay, so if you, for example, gave just one number, that probably is the number that you're talking about here. You waited until all the answers came out, and then you counted how many were correct. So if you just got one number, that's probably the number that you get here. This is the p-value, this is the r value. Okay, but I really want to know how is your p and r changing together. You see that? Okay, so you learn to write precision recall curves, learn to draw precision recall curves, learn to use those to figure out the true quality of an information retrieval system. So here's a simple example. These are basically called the 11-point precision recall curves, but really it's like you draw the recall here, precision here, and precision recall is between 0 and 1, precision is between 0 and 1. They call it 11-point because in the old days when everybody used to do this by hand, they would just put 11 points, 0, 0.1, 0.2, 0.3, etc. up to 1.0. Okay? So you now just give it to Excel. Here are the precision points, and for each point, you let the IR system start running, and every once in a while you stop it, compute the precision and recall. At that point of time, that will be an XY point. Okay, so here is an example. You should be able to do this. You'll do it yourself. Homework too. Suppose I ask some database, some IR system a query, and it turned out that it kept returning these answers: D1, D2, D3, D4, D5, blah, blah, blah. Now it turns out that the blue ones are the relevant ones. The Oracle told me that the blue ones are the relevant ones. Actually, eventually the user found that the blue ones are the relevant ones. Okay, so the question, of course, is, and assume these are the only ones. So, for example, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Only 10 relevant documents to this query. It turns out that's the total number of relevant documents. And they're being sent like this. Now, clearly you can tell that a much better system would have just given a D1 to, all the blue ones up front, and then put all the junk afterwards, right? You can tell that. Clearly you can see that. But the question, of course, is there are multiple ways of distributing the good answers over the bad ones. And you can actually talk about how the precision and recall are varying. So in this particular case, I can say, so for example, you assume that if you don't speak anything, it's 0 by 0. But we'll assume that's 1. Okay? And so if you haven't spoken anything yet, I'll give you the benefit of doubt and say when you start speaking, you will make sense. So precision always starts at 1. Okay. Now, if I, for example, were to the third document, if I go up to the third document, by this time the system returns 3 documents, of which 2 are relevant. So its precision is how much? 2/3. And it returned 2 documents. The total number of relevant documents are 10. So its recall is 0.2. So I have a number here, XY pair, 0.2. So you get the drift now. So you should be able to draw this curve. Right? Okay? So I have a precision recall curve, and I get to be able to look at this and say, looks like this guy has a reasonable precision, but as the recall increases, his precision seems to fall down. That's normally true mostly. So the question then is, if I give you 2 systems which have 2 precision and recall curves, what can I say about them? And this is again, I mentioned this in the beginning of the semester, the second class or something. But as I said, the dominance is useful. So for example, in these 3 colors, so these are corresponding to 3 different methods for IR. Okay? So if you ever find yourself paying good money for method 3, you didn't learn a thing in this class. Right? Because method 3 is dominated by method 1 and method 2 everywhere. Everywhere. It has low precision and low recall. That's like saying, get me, I like costlier tickets that let me, sit in the plane for longer times. That sort of makes no sense to most people because they want, to reduce both the time of travel and the cost of travel. And similarly, here you want to increase both the precision and the recall. So this is definitely dead case. What's interesting is these two. In this case, all you can say is that this one, the red one, seems to have higher precision at lower recalls. Because the red one is dominating the green one on this side. And it seems to have a lower precision eventually compared to this guy. Right? So you could say something interesting about them other than saying one is red and one is blue. And one is orange and one is blue. Okay? Now, of course, which one would you prefer? It depends on whether you want higher precision at lower recall levels or higher precision at higher recall levels. So you notice that if you run both these systems all the way down, at this point you would have thought the blue one is better than the red one. Okay, but actually for most of the time, in fact the red one is doing better than the blue. Okay, so this is like your hare and tortoise. Okay, so the red one is the hare. It starts very fast for precision and then slowly loses its precision as the recall increases. And this is your tortoise, which basically starts at lower precision, but it keeps the precision up as it goes on. So, if you just look at the last part, if the race goes to the final point, right, then obviously the tortoise wins. Okay, that's how we run Olympic races too, that the guy who reaches the final point the fastest wins the race. Even if in fact, there are all sorts of horse races and human races where for most of the time somebody else is winning, but all that matters is who actually crossed the final point. However, I'm saying that's what I would say, but in this case actually we actually do care about who is winning in the beginning. Because if you're a search engine, the fact that eventually you have a higher precision when the full recall is attained is not enough because most of your users would have left the room by that time. You want higher precision up front. Okay, but having said that, also keep in mind that the ones which give high precision up front probably are not giving you high recall eventually. Just like that conference analogy. But that's what everybody goes for because, forget about being the best search engine for eternity. First, we need customers. And if the customers are leaving, then it doesn't matter whether I'm the best search engine or not. So you'll wind up tending to, since you show top 10 results, you want to kind of tag the top 10 results with good results. Now, the interesting thing is, remember I told you about InfoSeek, which would show the top 10 results, and then say, if you want the next million results, pay me $10, I'll give it to you. And this happened less than, 8 years back. So we are that clueless. We, the human race, collectively are that clueless. It looks obvious. How could it be thinking that it would make sense? You should back everything up in the front. But what's obvious to you today is not obvious to anybody, who's trying to make money 8 years back. Okay? So that's the precision recall curve. Now the other interesting question is, of course, this is all this sort of qualitative way of figuring out which is better or worse by looking at the curves. Okay, but what if I want some sort of a single formula which combines precision and recall into a single number? Do you understand what I'm saying? Okay, then there are two cases. Case one is, suppose I only have a point-wise precision and recall. So I have P1 R1 and P2 R2 for two search engines at the end of their run. And I want to just come up with some single number for representing them.
Average.
That's the averages. The question, of course, is which average should we use? And as I mentioned again last time, the right average is the harmonic average because both the arithmetic average and the geometric average have this very bad property that they don't differentiate between 0.5, 0.5, and 0 and 1. At least arithmetic doesn't. Okay? So actually, if you have, the last time you probably remembered, harmonic mean is this problem. When those of, I mean, I'm sure most of you are out of high school for long enough that you probably forgot this. So if you travel at 40 miles per hour on the way out and 60 miles per hour on the way on the return, what's your average speed? It's not 40 plus 60 by 2.
It depends on the time, not on the space.
So that would be the harmonic mean. Because I said return, right? So I went to Tucson at 40 miles per hour. I came back from Tucson to the same point at 60 miles per hour. So what is my total average speed? To do that, essentially the average speed would be the harmonic mean of 40 and 60. That's when you actually first heard of harmonic mean. Because you've forgotten this. Okay? But now we use harmonic mean to combine precision and recall because that makes sense. You know, it has the right property. Now, you can also actually, so basically, so that's you know, it's like half of 1 by p plus 1 by r is equal to 1 by f. That's what you want. And this is, traditionally, this has been called the f measure. The harmonic mean has been called the f measure. Don't ask me why, but that's what you're supposed to remember. If anybody says f measure, they mean combining precision and recall into an harmonic mean. Okay? And so obviously if you simplify that, I'm going to pr by p plus r. And one other interesting thing is you can also have, just as if you have an arithmetic mean, you can have weighted arithmetic mean. You can also have weighted harmonic mean. Okay? And the weighted harmonic mean essentially gives like a beta weight to 1 and 1 minus beta weight to the other. And if you use that, then it will be a f beta measure. Okay? So there are, you know, f measure is the usual way you put a single point precision and recall comes into one number. Now, if you want to look at the entire curve, because this one would be able to say the f measure for this is at this point is one thing, it's different here, it's different here. So I can now plot the f measure itself at different recalls. But that still doesn't tell me which is winning, you know, if I look at the entire curve. So the thing that makes sense for the entire curve is the area under the curve. The area under the curve. Because remember, the most useful precision recall curve will always be like this. It holds the precision at 1 all the way to recall 1. So then the area is, this is the maximum area anybody can get. So there is an upper bound. So now you can compare everybody else in terms of the area under their curves. And that will also give you a good enough idea, an interesting idea of, you know, who's doing better. Okay, these are all different ways of understanding what to do if you have two different systems with different precision and recall as the recall values. Any questions on this one?
Is it possible for precision to go up with time?
Is it possible? Yeah, it is possible. I see students all the time in my courses whose precision increases as time goes on. And especially if you teach early in the morning, precision goes on, you know, even for me, because I start making nonsense and then as I wake up, I start making sense.
For search engines, not for students.
For students, professors, everybody. And in fact, even for the search engines, you can have low precision improving and then falling down. You can make a search engine which has every possible characteristic. You see what I'm saying? All sorts of crazy things are possible. So that's why I really want to think of it as a curve and area under the curve. Okay? Okay, so combining precision recall and that thing is over. So as I said, on the web, you probably are more interested in the precision because people want to see the first page, and if they don't get enough results, then they're not going to wait around to see maybe you will say good things by the end. So you lose customers beforehand, even if in fact eventually you win. Right? I mean, this is also true, by the way, in sports and games. I guess like the running in Olympic race takes like microseconds these days that you probably wouldn't have walked out between the during the race itself. But anything that takes time, I'm sure there have been baseball matches where the fans are left in disgust thinking the home team is losing, and then in the end, the home team somehow won. So they basically had low precision, but in the end, they reached, they did win the game. Right? So that is quite possible, but that's, you will still lose fans, just as you will lose customers if you're a search engine, if you don't do well in the beginning. Okay. Okay, so that's about if you were lucky enough to come up with the information retrieval algorithm, how to evaluate it. And we also talked about track competitions which actually evaluate real systems. So what I want to talk for the next half hour, a part of it again, is how do you go about designing retrieval engines? How do you go about designing information retrieval systems? And remember, it's an ill-specified problem, right? It's an ill-specified problem, I mentioned that. That basically means the user is giving a query, and the user is giving a query which is probably imprecise, and you're still supposed to show documents to the user that are likely to be relevant to the user. Okay, so my question in this slide really is how do I actually what I do want to do is get rid of this. Okay, so we want to rank and return documents that are relevant to the user's query. Right? That's what we want to do. The more relevant documents we can give, the higher our precision and higher our recall. That's a good IR system. Okay, so the magic word is finding relevant documents. Right? So if suppose each document has a relevance number R associated with it, then this just becomes a sorting problem. Right? Just put the ones with the higher relevance up and lower relevance down. Be done with it. Okay, so I really would like to act as if there is this function called R, which will give a number. And then I just sort the results using that number. That's what we want to do. So 2 questions. Question 1, what does the function depend on? Question 2, what is its closed form? In fact, question 2 is what I really want, but one way of finding, this function R is some random function. I'm trying to figure this out. That's all I want to figure out here. If you tell me this is the function, then I would be happy enough. Okay? But if you don't yet know how to go about looking for the function, you can at least ask yourself, well, what would this function depend on? What would be its arguments? Okay? So I want to first discuss what should be the arguments of this relevance function. And then discuss how to compute the function itself. Okay, humor me because I know some of you are probably dying to say, when is he going to get to vector similarity? We'll get there soon enough. The question is, we want to know why the activity we think vector similarity will solve this imposed problem. What's the right way of solving the problem first? And then, how do you optimize it to something that will work? My usual way, if I haven't already said this in this class, I normally say it pretty much the first day. My difference between a computer scientist and a programmer is a computer scientist understands how to do things right and then gives up doing on them right because it's too costly. Programmer just makes something and says, it works, why do you care? Programmers might make just as much money as computer scientists, maybe more. But computer scientists actually know why they did it. This is what they should have done. Did I do that? Or if I didn't do it, why did I not do it? There must have been a good reason, some complexity reason, some knowledge acquisition reason, something. That's what I want you to understand on this one. Okay, so tell me what should R depend on? R is a function of some things, and the function will give a number. So what are its arguments?
The query.
Okay, so let's write it down. So you want to say R is a function of the query Q and the document D. And what else? So in fact, it's useful to write R in this form D given, because eventually you are giving the relevance for a document D based on, presumably, you want query Q. Anything else?
The universe of documents.
Universe of documents. That's a very good idea. Okay. Document universe. What else?
The user.
User. Okay. exercise worth doing. Because once you stick to an answer that seems to be working, that's the worst thing. That has the worst effect on your intellect because you'll never look for anything else. Okay, so you should know why you got into the similarity stuff. Okay, so really it should be documents, the queries, the universe of documents, which is sort of a reasonable thing to talk about, and the user, you. It should depend on the user, you. Interesting, right? Okay, then what else should it depend on?
Yeah.
Yes.
Yeah. The user universe.
What? The user's universe. That's user. Yes, it's a good point. That means if the user doesn't even have certain documents in their universe, they didn't expect to see them then. But to some extent, that is a kind of definition of the user. Okay, again, remember, all I'm writing here is document D. I did not tell you how the document is represented. Right? In fact, we'll talk about how these things have to be represented, and each way of representing gives rise to a different way of assessing the relevance function. I didn't tell you how the D is represented. I didn't tell you how the Q is represented. Maybe Q is represented as just the keywords. Okay? I did certainly not tell you how the user is represented. Yes?
The trustworthiness of a given document?
Okay, that's a good point, but I would say that in traditional IR, everything is considered equally trustworthy. So that is more for the second half of the IR lecture. Okay, so you really did not, you had no reason to believe that one document is any more trustworthy than another document. They all have ISBN numbers, they are in the library. So they must all be right. Yes?
The number of times the keywords occur and how they occur.
Why? I don't know. I mean, so the point is, that is already present in this information. If you were to care about that, I would say that you can get that. If I give you the query on the document, you can do, I didn't tell you how you're going to use the query on the document to figure out the R. There are infinite number of ways of using query on the document to figure out R. For example, sign of the document size divided by tan square of the query size is a function. It may not have a behavior function, but a function. Okay, so don't think about how to use them. First think only about what the functional form is. And if you're not even having the arguments for the function, then finding the right form doesn't help you. The right formula doesn't help you because it's missing one of the most important, one of the things. So for example, if a search engine ignores the user, you should all be able to tell how it will fail. Right? Because like presumably you said you because you're saying just given a query, it's not obvious whether a document is relevant to that query or not unless you know the user. Right? Okay? That's, by the way, true, right? I mean, do people actually have enough examples of that? I mean, that guy wanted Ken, and Ken is supposed to be a particular set of documents for him. And I may have mentioned Michael Jordan query. Now, Michael Jordan, basically, if I say Michael Jordan, most search engines will give you pages and pages of this guy, obscure player who used to play some sort of a ball game, right? And but the one that I'm really interested in is the machine learning researcher who has done really neat work on search engines. Okay, so what's relevant for you is not relevant for me. But do search engines care? No, not, I mean, at least up front, if I just log in, I mean, if I don't log in and I just ask the query, they don't know. Okay, and so they will still, even now I have to go through, finally I have figured out what this Michael Jordan guy is all about, the other guy. You know, I know the machine learning guy, but I have to figure out the ball game guy because he keeps showing up whenever I search for the other guy. Okay, so user matters. And similarly, query matters, and similarly, you know, I guess document user, universe matters. I want to see anything else. Yes?
Maybe something like, who else is saying this document is relevant?
Who else? What do you mean who else?
It means like, in a calculator, when you verify a calculator, you...
No, again, don't talk about verification, trustworthiness, etc. These are all library books. They're all God-given truth.
What about what the user actually needs?
Well, that's what you're trying to compute. Presumably, this representation should have enough information about the user such that you can figure out, including brain tissue from the user. You know, so that could, I didn't tell you should not take that, right? I mean, user could be just the user's name or a specimen of their brain tissue, and you can decide which function you want to compute. Somebody who hasn't talked yet. Yes.
When you say the document universe, do you mean like the history of documents viewed by previous queries?
Actually, of these, you know, I basically talk. Okay, so what did you say?
Well,
Not quite. Okay. So here is what I will show you.
It should be what I need.
So there should be document D, the query Q, the user U, that much you agree. And what else? I'm saying this again, I don't know why. But the most important query in the world, which is my name. Right? And as far as this class is concerned, that's like the most important query. So you say common body, this is not today, but a couple of days back, I guess. And then, obviously I come first for a query common body. So far, so good. What's wrong with this picture? This is me, the most important common party. This is my papers, the papers of the most important common party. Who is this guy? Who is this Ravindranath common party guy? And then again, we come back to the right track, my papers on DBLP. And then who is this Krishna common party guy? Who is this Uma Sharada common party guy? What are they wasting valuable space in the top 10 results? Do you understand what I'm saying? If in fact you believe that the most relevant result is Subhara common party, if you want to give top 10 results, you should give top 10 copies of my page. And then you won't have any users other than me. Right? So, what matters is the sequence of results you have given up until then. The relevance of a document depends also on the list of the sequence of results you have given up until that point. You tell a joke, it'll be funny. Tell the joke second time, people will start squirming. The 20th time, they don't seem to be interested in laughing. They're interested in hitting you. Why has the joke lost its relevance? It's the same relevant joke, and in fact, your function would have said the joke is pretty darn funny. Because it only depends on the joke and the people. And the people are the same, the joke is the same. What's wrong? Just you told it too many times. Okay? And so my point is that, in fact, you also care about the documents that have already been shown until now. You won't think about it. Search engines have to care about this. That's why they don't show you all my pages when you say common party. They still show all Michael Jordan, the ball players pages in the top 10. But in the top 1,000 or so, they start talking about this other Michael Jordan, who is, the machine engineer. Okay, so they are sort of diversifying the results. And to some extent, there are multiple good reasons for doing this. One is because actually you don't know who is the user. And so if you don't know the user's profile, then you are better off diversifying the results. You want to show some of this Michael Jordan, some of the other Michael Jordan. And second is, even I, who really love my page, might probably get sick and tired of it if it's all top 10 results are just that page. So I would also say, maybe top 10 is okay. Top 20, I will start, finding that it's not relevant anymore. Okay. So my point is that if you are in the context of, if you're talking about the form of the function looks like this: relevance of a document D, given query Q, user U, assuming the same universe of documents. Assume that all the information engines are using the same universe of documents. Then a document D, given query Q, user U, and the sequence of documents you have seen until now.
Yeah, what I meant about that one was, suppose you need to find something about integrals. And in the universe of documents, you only have a lot of things that doesn't talk about math, and just one that talks barely about math. That one in that universe is very relevant.
But that's fine.
But if you change the universe, it's no longer relevant anymore.
Well, yes, but you could have done this. You could have done this by saying the one about integrals, you have queries about integrals. Nobody stops you from saying the highest relevance you gave to anybody is 0.0001. And when you start it, it will still come at the top. Do you understand what I'm saying? In fact, you would be surprised at how many systems work that way. So how many of you have been using speech recognition systems? You call any phone these days, it will try to talk to you, right? And it will try to make sense of what you're saying and say, repeat yourself, please, blah, blah, blah. And they are essentially trying to listen to what you said and say, did you say this? Right? So clearly, of the number of the number of words that you can be speaking, basically they're trying to compute the probability of each of those words based on the speech signal they got. And they're picking the one with the highest probability. What do you think is the typical highest probability for a winning word? Is extremely low. 10 power minus something most of the time. It's just that it's the winner. This is the classic relative grading. All of you can collude and do really, really badly,